Okay, so in this video we're going to do extra examples of the rational root theorem as well as some factoring as it comes up. Again, I'm going to do the highlighted problems for practice. So I'm going to do this one, I will do this one, and I will do this one. And then the other two you will do as extra practice on your own. You can find this worksheet on Schoology. So let's get started. So I'm looking at this problem, and I'm going to kind of walk through the steps I should think when I'm trying to factor something. Step number one, always, is there a greatest common factor? Is there a GCF I can pull out? No, there is not, so I move on. The next thing I look at is if I can do something easier before I do P over Q. So if I try to group, I notice that I can't really factor anything out of the second group, so that's not going to help me. It is not a difference or sum of cubes because there's more than two terms, there's four. So last but not least, I got to do P over Q. So again, P is the constant term, so my factors of 15 are 1, 3, 5, and 15. Well, I'm writing kind of small. And then my factors of Q are just 1. There's only a 1 in front of the 3. So when I do P over Q, I get plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. You do all of the P's divided by all of the Q's, which is pretty easy because Q is only 1. So you have 8 possible rational roots. I kind of already did this problem, so again, just for the sake of the video not taking 3 hours, I will be plugging in the number that I know that works. So I know that 1 works, and a lot of you guys keep asking me, well, is there a way for me to know right off the bat which one that works? And the answer is no. I wish there was. This is a very guess and check method. If there was an easier way, believe me, mathematicians would be very, very happy. So you bring down the 1. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. Negative 17 plus 2 is negative 15. Negative 15 times 1 is negative 15. 15 plus negative 15 is 0. So now I know that x minus 1 is a factor. And from here, I'm going to write that as a polynomial, 1x squared plus 2x minus 15, because I started with a degree 3 divided by a degree 1, so it becomes a degree 2. Now, you can use whatever method you feel comfortable using to factor this. It could be the Mr. Rat box way. It could be the X, which is factoring by grouping, or FML, as Dresden calls it. Or me, I'm going to do it in my head. Some of you also can do it in your head, but a lot of you can pause the video, double check what you get with what I write down, which is x minus 3, x plus 5. Therefore, my roots are 1, 3, and negative 5, all multiplicity 1. So somebody asked when they talked about extra examples to explain multiplicity one more time. And multiplicity is how many times a 0 happens. It matches the degree. So if we look at the factored form, so I'll label all the parts. This is factored form. When we look at factored form, they all secretly have a degree of 1 because they only happen once. Therefore, they all have a multiplicity 1. Here, we would call these our roots or zeros or solutions. And here, if they're written as points, are the x-intercepts. Now again, I'm just trying to show you all the different words for the same thing. So, color that in. This is factored form, and that tells us where the multiplicity comes from. And this is x-intercepts, because they are in point form. So let's try this next one. This is a degree 5, so it's a much bigger one, which means I'm definitely going to have to do P over Q a couple times, but I'm always just going to double check. Because there's an even number of terms, I can check if grouping works, and it definitely doesn't. What the heck am I going to factor out from 61 and 20? So, nope. That means I have to do P over Q. P, Q, P over Q. So, factors of 20 are 1, 2, 4, 5, 10, and 20. There's a 1 in front of the x to the 5th, so that's all I have to deal with, which means I do plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. Great, so now I start my P over Q process. Move over here. Again, I did this problem before, so that's why I'm going to have these lucky guesses each time. But I'm going to start with the coefficients. 1, negative 2, negative 20. I make sure I have every degree represented so I don't have to add zeros. 62, negative 61, and 20. And I happen to know that 1 also works for this one. I'm going to try to save as much room as possible because this problem is we're going to have to do P over Q a couple times because we're starting with a 5th, and we only stop P over Q once we get to a squared. So we got to do it lots. So I bring down the 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times 1 is negative 1. Negative 21. Negative 21. This becomes 41. This goes up here, 41. This becomes negative 20. Negative 20. 0. Okay. So again, a degree 5 divided by a degree 1 becomes a degree 4. So I know that I'm going to have to do P over Q again. Remember that our tip is if it did not work the first time, it will not work the second time. So if you tested something like 2, it wouldn't work. So it's not going to work again. However, 1 could work again. So let's try it. Okay, so I bring down the 1. 1 times 1 is 1. 0. 0. Negative 21. Negative 21 becomes 20. Oh my gosh, look, it works again. It's almost like I designed it that way. Who'd have thought? So then now I've divided a degree 5 twice. So degree 4, degree 3. So got to do it one more time. Got to do it one more time. Might as well try that one more time. So then you bring down the 1. 1 is what is 1. Then 1. Then 1. Then negative 20. Negative 20. Hey. 0. Holy moly. 3 1s? So if you write this, you x minus 1 cubed, because it happened 3 times. 1, 2, 3. And then x squared plus x minus 20. So again, you're going to have to decide what way you want to factor the quadratic one. So take a minute, pause it, and factor it. And if you're coming back, or if you factor really fast, you know that that's x plus 5 and x minus 4. Therefore, I have x equals 1 with a multiplicity of 3, because it happens 3 times because of the degree, and I have x equals negative 5 and 4 with a multiplicity of uno, because they both happen once. And again, we can always double check. Because I have 3 1s, I have 1 5 and 1 4, that's 5 roots, or that's 5 solutions total, which matches the original degree of the problem. So I know I did it correctly. Next, we're kind of going to move on from the P over Q and try some difference of squares. So here I have a binomial that's in the form, I know that x squared is x to the 4th, and 4 squared is 16. Therefore, I can write this as x squared minus 4, x squared plus 4. I can also recognize that this one over here is another difference of squares. So you get x minus 2, x plus 2, x squared plus 4. And now, if I wanted to find my roots, I can do x equals 2 from this one, x equals negative 2 from the second one, and then I have to solve for this one. X squared plus 4 equals 0, x squared equals negative 4. Oh good, some imaginary numbers. So you take the square root of both sides, and you get x equals plus or minus 2i. So my roots are 2, negative 2, 2i, and negative 2i. All of them have a multiplicity 1. All mult 1. If you had to write this completely in factored form, I would either accept this, or, oh, there's a little squiggle, or it can be x minus 2, x plus 2, x minus 2i, x plus 2i. So that is where we factor with some imaginaries involved, and that's using a tool that's not P over Q. Technically, you could use P over Q if you added all of the zeros. It would just take a little longer. And last but not least, one of these funky to the 4th ones, but it looks like a squared. So we're going to do the factoring by a cross, but I'm going to use Dresden's terminology instead of mine. So this is the first term, the middle term, and the last term. So FML. I'm going to set up my cross. You do the first term and last term on top, and the middle term on the bottom. So the first term times the last term is 4x to the 4th, and negative 4x squared. So what multiplies to this and adds to this? Negative 2x squared and negative 2x squared. So I'm going to now factor by grouping. So I have x to the 4th minus 2x squared minus 2x squared plus 4. I group these two together, and I group these two together. From the first two, I can factor out an x squared, and I'm left with x squared minus 2. Out of the second one, I can factor out a minus 2, and I'm left with x squared minus 2. So this becomes x squared minus 2 times x squared minus 2, or x squared minus 2 squared. So now I need to find my roots. So x squared minus 2 equals 0, x squared equals 2, x equals plus or minus root 2. So notice that I'm just showing you that roots and imaginary numbers always come in pairs. But this didn't just happen once. It didn't just happen once. It happened twice. So both of these have a multiplicity of 2. And that could either come from the fact that you can visually see it happen twice, right here, or because it has a degree of 2 on it. So that is the end of all of the extra examples for the complicated factoring. Try the other two on your own. This worksheet is on Schoology, so you can check your work. Thank you. Have a great day.